Now I'm quite flustered. Right, so if the session is now being recorded, so let's just jump in, and what we are going to discuss is this constant mass-based CP issue that people doesn't, they have issues with that. So let's just take our the online test. So I'm just going to, those of you who don't start, spoiler alert, you were given the reaction that you are supposed to analyze is 2A, that goes to B plus C. And in the problem statement, all I say is that you may assume that del CP of the reaction is equal to 0, right? But let's now just say, what does that imply, and what is the implications of this del CP reaction that can be taken as 0? So if I should take let's say my mole mass of A. So first off, let's just give mole masses. This problem will be alleviated when we start working with real life components, and you can find their mole masses and their CP values, actual CP values. But just for illustration purposes, I'm now going to say a component A has got a mole mass of 50. Which means that the combined mole mass of B and C must add up to 100. So if I have the mole mass column for each of them, let's just say I'm going to choose this one to be 30 and this one to be 70. And I choose a CP value for each. I'm now just going to randomly choose a CP value. So this CP value is 30, and this is on a molar basis. So this is in joules per mole Kelvin. So what the CP of C plus the CP of B must then add up to 60 in order for this del CP to be equal to 0. Do you agree with me? So if I just look at the reaction stoichiometry, this times CP of whatever C is CP of B minus 2 times the CP of C must be equal to 0 for del CP of the reaction to be true. And now when we are saying that the del CP is 0, it means that each carbon molecule takes with it its own energy carrying capacity. Each hydrogen molecule. So which means that the energy carrying capacity, or the CP value, is distributed to match the molar masses. So therefore, if I want to calculate the CP value of C, it should then be equal to 70 divided by the total molar mass times that 60. And this one CP value must be 30 divided by the total molar mass of the mixture times 30. Right, so you can now take your calculators and give values for these. So this is a 0, and give values for these numbers. But now I've got these CP values in terms of the molar masses, and in other words, it adds up to that 60 value. So what this molar mass and the CP value are not disconnected when we make this del CP, when we apply or we assume that that is true, because we have got a larger molecule, it must have the larger CP value. We've got a smaller molecule, we must have the smaller CP value. So if I now employ this, and I want you to test this now, if I now take the CP values and I want to calculate the mass-based CP value of each of the components. So that is going to be 30 for CPA divided by 50, which is going to give me 0.6, right? If I'm going to apply it here, so you can do your calculations. If I take this CP value, the 30 over 100 times 60, sorry, that must be a 60, that must be a 60, and I divide it by the molar mass, which is the 30, I'm going to get 0.6. And this is 70 over 100 times 60, it is its CP value there, and I divide it by its molar mass, which is 70, I'm going to end up with 0.6. So the mass-based CP value of each of the components is exactly the same, because we say that we are going to divide it, this is carbons and hydrogens and oxygens and whatever, carbons, hydrogens, oxygens. So if we appropriate a certain amount of that CP value to each of the atoms that form part of that molecule, and we just say it takes with it its CP value, the change in the bonds doesn't change the CP value. This is what ends up happening over here. So the mass-based CP value of each of the components is then the same, and I don't change the MCP value. So MCP, if I want to heat up stuff, whether I'm heating up products or reactants, it's going to be exactly the same, because the mass must stay the same, steady state. Mass as the reaction takes place must stay the same. And now I'm also proving that the CP value stays exactly the same. The mass-based CP value stays exactly the same. In real life, this mass-based CP value will differ slightly. So this is still going to be true. The molar masses must still, the molar masses must still be, must add up. So I must still have a sum of molar masses on this side must add up to the molar masses on the left-hand side of my equation. But for the CP values, this is not necessarily the truth. So it doesn't need to add up to that, because the fact that the carbon is now bonded to an oxygen, or it's got a double bond carbon, may mean that it changes its energy carrying capacity slightly, but not by that much. So that is why that is a very good, often a very good assumption to make, is that this del CP is equal to 0, therefore the mass-based CP value of each of the flowing streams stay exactly the same. So what you can now do is, if you want to pause and you can read or maybe listen through what I've written, this is nothing different on the whiteboard and on a blackboard with chalk. I realized that I write illegibly. So if you didn't listen, you wouldn't be able to read. But what you can now do in Excel somewhere is to say, okay, if I've got a conversion now, let me take a conversion of, let's say A. I start with pure A, and I convert 50% of A. If I make this 0.5. Build an extra line here, where you now say, okay, so if I start with, let's say, 5 moles per second of A, and I convert 50%, how many moles of A will I have left? How many moles of B will I form? How many moles of C will I form? And then you calculate, just if I now take Fi naught, which is just my A coming in, times its CP value at the start, at the inlet, and I calculate using the molar flow rates of each of my different components using my XA and their CP values that I've assigned to them. And then you will see that each of them must give exactly the same answer, because of what did I write that? Because the mass-based heat capacities is exactly the same, and the molar masses must add up to the total molar mass. Left-hand side, right-hand side must be equal to each other. Does that make sense? Who asked that question? I think Devold had a question about this. Can you just maybe, Devold, I don't know whether you're here. Questions on this? No. No. So let me just see. Does this mean that the reaction is, that says nothing? Listen up. So the CP value, let me clear so that we have no confusion here. If we now have the CP values, so a del CP of a reaction and a del H of a reaction is two completely different things. This thing just tells us how does the enthalpy change if I change the temperature while I keep the pressure constant. This del H reaction is at a pressure and at a temperature. How does the enthalpies change? So there's no change in enthalpy. How does the enthalpies change if I take 2A that goes to B plus C? So they are not related in that sense. Where I use the del CP reaction with del H reaction is, and this is a whole derivation, it's a whole few pages in Smith, Van Ness and Abbott, is to say at any temperature I can relate del H reaction to a reference temperature value. The reaction at a reference temperature plus del CP reaction times that T minus the reference temperature. So I can relate how this will change with a change in temperature so I bring in the CP value to account for the fact that I'm not considering this just at one temperature, I want it at other temperatures. But it does not say anything about the exothermic or the endothermic, nor the endothermic nature of my reaction. Okay, right. Dewald, thank you very much. Okay, so yes, Philip, go for it.
Ma'am, sorry, just to confirm, the CP values in mass units will therefore stay the same, but that's not necessarily
Yes.
true for the CP in mole units.
Okay, so let me just try to say this in a different way. Let me just clear it. So if I have, once again, my 2A that goes to B plus C, the CP value of B is not equal to the CP value of A. The CP value of C, mole base, so it's joule per mole Kelvin. CP of B is not equal to A. CP of C is not equal to CP of A. But the sum of the CP of C plus the CP of B will pretty much add up to be 2 times the CP of A. Right? But if I calculate the CP values, the mass-based CP values, the CP mass-based of A is equal to the mass-based CP value of B, which is equal to the mass-based CP value of C. This is what this assumption implies. Mass-based, they're exactly the same. Because since this is let's just say it splits equally. So this has got a molar mass of 50, A. It's got a molar mass of 50. Then this must be 50 and this must be 50. And then their CP values, and this holds only if del CP, yes. So this holds if del CP reaction is equal to 0. So what I strongly recommend is just once, go to an Excel spreadsheet, make sure that you've got a reaction. What we do know is that the molar mass on the left-hand side must be equal to that on the right-hand side, because the mass balance must balance, and that will not be true if that is not the case, right-hand side. Okay. But the CP values does not have to follow that, but it very closely follows that, in that the larger molecules will have a larger energy carrying capacity than the smaller molecules. If I take hydrogen or I take air and I compare their CP values, I will see that hydrogen has got a much lower CP value than air, for instance. And since I have the same stuff, the same building blocks, I've got carbons, especially if I've just have hydrocarbons forming hydrocarbons, other hydrocarbons, the chances that del CP of the reaction is pretty much equal to 0 is fairly large. It may be have a 5 joule per mole difference or a 10 joule per mole difference, and compared to my del H reaction, which is then, let's say, minus 50,000 joules per mole. That change in del CP value from left-hand side to right-hand side becomes really, it doesn't really make a significant difference in your analysis. Okay, Philip, happy?
Yes, thank you, ma'am.
Yeah, so sorry. Stoichiometric numbers, of course, missing there. Thank you very much, Luca. Yes, we must be clear about that. But, go and find a real-life reaction. We're going to have some real-life reactions after semester test 1, I promise you. We're going to get rid of our A, B's, and C's. So that you can just see this when you have actual molar masses of a benzene and a styrene and a toluene, and you can apply this in a table, in a spreadsheet, or in Python to see this is what we are talking about. Okay. More questions? Happy? All right. Okay. So let's clear this up. Then I had a question about the energy balance, and the energy balance, the paradigm, the way you think about the energy balance. So many people said, okay, so it's especially when we started with the non-adiabatic stuff. So we had Q, and we have energy in with mass, and we have energy out with mass. And we've got a temperature in, and we've got a temperature out. Okay. And then we have the temperature. If it's a CSTR, for instance, the temperature out and the temperature where the reaction takes place is the same. If it's a PFR, there's a gradual change in the temperature inside here. But if I want to do my overall energy balance like that, I had lots of people and many older textbooks and professors actually use this formula for energy to say I've got energy coming in with my inlet streams, energy in, and I've got energy that I take out, and I've got an energy generation term due to a reaction, and that must be equal to Q. So my critique against this is it goes against the energy balance. We do not, that's the first law. Energy generation and saying that the first law applies is like in, what the hell are you talking about? So it doesn't make sense to me. So, and if you reconcile it with the energy balance that we did in CTD, this energy coming in with mass, energy going out with mass, this part that you want to associate with a del H reaction term, that is inherently present in the energy that comes in and goes out. So if I now, I hate this eraser. If I now want to have an energy, do that energy balance again, and I've got streams flowing in and I've got streams flowing out. Remember, what does the stream bring with it? What energy packets, if I now should take you back to your second year, first lecture or second lecture, somewhere there. It's got its internal energy, it's got the PV part that is in order to flow, to force it to flow, and that is its enthalpy. It brings with it its kinetic energy and its potential energy. The stuff going out takes with it those same energy components, kinetic energy and potential energy. We neglect these terms, right? Why these energy terms can change is very closely related to that, the change in the internal energy. Okay, so the change in the internal energy and of course the PV combination, more important for gases, is because there's a change in the bonds and the temperature and the pressure affects this parameter. If it goes out as a different combination of carbons, hydrogens, and oxygens, this will be different because a change in the bonds, a change in the temperature, a change in the pressure, blah, blah. So there's no energy that's generated. This comes in at a certain state, it goes out at a certain state, and inherent in this enthalpy that comes in, sum of all the enthalpies that goes in, minus sum of all the enthalpies that go out, plus Q must be equal to 0 in our energy balances. So in this is the change in enthalpy due to the reaction. So if you do the math, it boils down to exactly the same equations. But the approach that most of the modern textbooks recommend is to get rid of the confusing aspects of having a del H, an energy generation term due to a reaction. And to say that these two terms, we would rather account for it by having, and this is what Aspen will do, or DWSIM, I'm not sure what you will be allowed to use in your final year design projects or in CPS, is if you do an energy balance, what Aspen does is it goes there and it says, what do I have? I have oxygen, I've got some carbon, methane, and over here I've got oxygen left, I've got carbon dioxide, I've got carbon monoxide, and some uncombusted methane at a certain temperature. Let me go to my database and let me find the enthalpies of all those components, find the enthalpies of all those components, and in that is built in the change in the bonds. And then, so you will be able to calculate that kilowatt value of the inlet stream and the kilowatt value of the outlet stream. And that will then be equal to Q if it's a non-adiabatic reactor. So then you would have specified this outlet temperature in Aspen or in DWSIM probably, so that it can calculate the duty of your device, your whatever unit operation. So the way we account for it is by, in this course, because we are not only interested in the overall energy balance, unfortunately, or fortunately, because we can have fun with it. We are interested in, specifically in a plug flow reactor, we need to know what happens here in the middle. We need to have a temperature profile along the length of our reactors. Why? Because the temperature seriously affects our rate. So we are not only interested in the duty of that thing that Aspen can calculate for us happily, but when you design reactors, Aspen cannot help you because you need the temperature profile through your plug flow reactor in order to compensate for the fact that I don't have a constant rate here. And in order to size my reactor over here, okay, you specify the temperature, calculate the duty, but the sizing of the reactor and what is the rate that must be available will be up to you. I'm not sure who asked this question. Sean, are you here, Sean? So I'll catch people if they don't get up early. Is that better? Yeah, hello. Okay, so Sean, give me a thumbs up or a thumbs down, then I will keep on talking. Sean is thinking, oh yes, it's a thumbs up. Anybody else with a question, raise a hand. Raise a hand. Okay, no hands raised. Right, so this is on the energy balance, just reconciling it with that energy generation term. That, you know, in many, I think Himmelblau actually in some of the versions still uses that. And when I was taught the energy balance in my second year, I certainly used the energy generation term. And when I started to do thermodynamics, it confused the hell out of me because where is that energy generation term? Right, so. Okay, so let's just now clear my page and Angelo's question. Save files and there. I'm going to use his image. Thank you, Angelo. Not sure whether Angelo is here, but this is this Taylor expansion where we now say that how can I assume, how can I jump from the fact that I just calculate the outlet temp. So let me just make a drawing on this. Oh, yes, I can. But it doesn't want to delete it. Oh, it does. If I have a CSTR reactor, and the CSTR we know operates at a temperature because it's well mixed. So I have the temperature of my reactor. And now I'm going to have a utility that I'm going to use to heat up or cool down that reactor. And it comes in at the temperature. So let's say I use it to heat up. So in other words, it comes in at temperature in and it goes out at the temperature of the utility out. And the outlet utility will be less than the inlet utility. When we out and UN, when we consider heat transfer, so we've got the energy balance that says Q must be equal to del H of my flowing streams. Okay, but now when I start designing the heat transfer devices, I need to compensate for the fact that this rate at which I want to remove heat must be you know, in your CIO design must be also be equal to how fast can I take it away. So this is what I want, and now I need to design my heat transfer stuff and in order to make sure that this actually happens. So if I have heat transfer, of course, that Q has a heat transfer constant, the rate kind of the rate constant for heat transfer. I need area for heat transfer, so that will be the area of my coil. So I'll have an overall heat transfer constant, and then I will have to, the driving force for heat transfer is what is the temperature difference between the stuff that exchanges heat with each other. That's what it boils down to. It's like the concentration. So I've got the volume of term, if I think about the rate of heat transfer and I want to relate it to a chemical reactor. This is kind of the area that's available where the heat transfer, I need lots of area for heat transfer. I've got a rate constant for heat transfer. How fast can the heat transfer take place in that area? And that has to do with the flow rates and the mixing and all the stuff that you encountered in CIO, I think, yes. And then I've got the driving force, which is the temperature difference between my reactor and my utility over here. And normally, you know, when we've got countercurrent stuff, you've got the log mean temperature difference equation, and this is where this comes from, that you want to calculate, not use it, because the temperature of the utility is not really constant. This is warmer and this will be colder. And now what Vogler says is, if I now, in that log mean temperature difference, use this Taylor expansion thing, let me just clear all my writing, and let's get to the, thank you, there we go. So if I have this Taylor expansion thing, I want to, in my energy balance, so this is the energy balance for the utility. Energy balance for the utility that says, and this is Q from the perspective of my reactor, because from the perspective of my utility, this is equal to but opposite in sign, so minus. Q that flows to or from the reactor is opposite in sign but equal to that flows to the utility. So this is Q of my reactor. So that's why it's got M of my coolant, Cp of the coolant, temperature in minus temperature out, and not out minus in, because it is negative Q from the perspective of my coolant. And now over here it replaces this using the log mean temperature difference and the fact that Q must be equal to a UA times that log mean temperature difference. It wants to eliminate temperature of A, utility, so Vogler uses A, in terms of the temperature of my reactor, right? So what it now says is, if I want to calculate this utility 2, and I substitute that in there, and thank you for Angela for doing the maths for us. If I substitute that in there for this exponent part, if I use my Taylor expansion and I blah, 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 wara, you can read the list. If I look at this equation, what Vogler says, if this MCP becomes really big, not only can I use this expansion, but if I've got a UA value, so if the heat transfer rate divided by the rate at which the stuff flows through my utility, if this becomes really huge, this term goes to 0. So that whole term becomes really small, like in a 0.5 or a whatever. And compared to my inlet utility temperature, this then becomes negligible. So if you want to visualize this, okay, so let me just, the math tells us if I make this really big, I multiply this difference by a very small number. So this becomes like a 2 or a 0.5 plus whatever my utility temperature is, like 300. And that change is negligible. That's what Vogler tells us we can do. And if we then look at our reactor and the rate of heat transfer, so we've got a heat transfer coefficient and we've got a temperature difference for heat transfer, then it says, okay, the difference is then a constant because my utility has got a constant temperature pretty much, and my reactor has got a constant temperature pretty much. So I can therefore use this equation for my heat transfer rate. So that is what it boils down to. It says you've put so much in there that the energy carrying capacity is so huge that it doesn't matter the amount of heat that flows to it. It can absorb it without really changing its temperature. So if I look at from the perspective of QC, and I've got M of the cooling medium, and I've got the temperature of, okay, let me just be consistent, utility, and I've got the CP value of my utility and temperature of the utility out minus temperature of utility in. So I've got a huge amount of Q, right, that flows in there, but this is so large that this difference becomes very small. Small enough to be able to neglect it when I calculate that rate of heat transfer. So let's check if Angela is here. Angela, happy? Ding, ding. Okay, maybe he's not here. All right, but I will force him to watch the recording. Okay, so any other questions on this? Okay, clear. Camille, Yuri. Speak up, Yuri. Or are you typing?
I can most probably speak today.
Yes, okay, I can hear you. Yes, go for
Okay.
it. Very brave. Thank you. Yeah, and for Yuri. Yeah,
So,
go for it.
at what ratio of utility flow would the increase in, yeah, this
Will it
is
be
why I don't
negligible?
speak. Yeah, when will it be negligible?
Quite often, this is the same scenario. I cannot give you the answer because it depends on your system and it depends on the energy carrying capacity. Okay, Yuri, your hand is still up. I think you must just lower it. So the energy carrying capacity, the CP value. Let me get a pointer there. Can you see the pointer or not? Anybody? No, probably not. Let me just rather get a. So if you look at the, nope, okay. So if you look at, let me just get something to write with then. The relationship between this and the value, blah, 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 the value of your inlet variable. So it all depends. It's like the same for the del CP. When people ask me, when does it matter? When can we assume it's equal to 0? If once you assume that that's the case, we have the equations to test it. We don't have to sort, oh, if that is true, like have a rule of thumb. There's no rule of thumb. You are looking for a rule of thumb. There are no rule of thumb, except to say, in this course, we are going to apply it. Just to make the maths easier, but there's no need because you can, in fact, substitute the whole equation in there. It just makes our energy balances for our CSTR reactors very nonlinear. And it's not as if you will not be able to solve it, but if you think you struggle with F-solve now and you take fine-tuning and you take it an hour to solve, it just makes it more complicated for no benefit in terms of your learning. Okay. So, but this is important to understand why we are making the assumption that we will always have a large enough MCP here so that this term goes to 0. Okay, so no rule of thumb exists. Okay, questions, more questions. Camille, are you going to speak to me or are you going to, we increase the tube timer, greater contour, shorter lengths and smaller maximum. What are the downsides to increasing the tube size? That's such a good question. I love questions like that. Let me just get a whiteboard. All questions are good. Don't feel bad about the other questions. Okay. So what else? So tube diameter, increasing the tube diameter. So let me just show you this. I had a few designs. And now I'm speaking from marking thousands of final year designs. If you build a reactor like this, right? This is that, or you can build a reactor that looks like this. Okay. Generally, when we build plug flow reactors or PBO reactors, and we want to use heat transfer. So one of the key aspects is, in fact, the fact that we want heat transfer in our reactor. So if I have a UA value, not only will the U be affected because of the flow rates in this huge reactor, in the big reactor, but also the heat transfer area that is available. So our heat transfer becomes much more efficient when we have a thinner tube. So in fact, it will always be a play-off between, okay, I will increase my pressure drop, frictional pressure drop. In this one, I'm going to have pretty much 0 frictional pressure drop. And in this one, yes, it's going to become more substantial and it's going to affect my conversion. But the fact that I can play with the temperature has got a much bigger effect than the pressure losses, right? So at the set, I cannot tolerate pressure losses that goes to, then it starts to, the sizing of my equipment when I have to drive the fluid through it. I need to take cognizance, thank you, of the effect of pressure drop. But generally, it will not be the game maker when I make decisions. It will not be the game maker when I make decisions. The game makers will rather be, I need to take it into consideration, but the game maker will be that and the heat transfer. So if you think about the heat transfer, what we are currently assuming is that if I consider the temperature over this diameter of my tube, so this is my tube diameter, and I've got heat transfer here at the wall, I assume that the temperature here in a slice, so it's not now along the length of a reactor. Do you understand what I'm? Please make sure it's along this, over this diameter of my tube, not along the length of my reactor. So this has got a long, this has got a very short tube diameter, right? Is I assume that I don't have any radial temperature differences, which implies that this temperature is constant even in the middle. The heat transfer is fast enough. So let's say I've got a very exothermic reaction. If I've got a very exothermic reaction and there it just wants to heat up more, and at the sides I've got my coolant there that can cool it down, but in the middle I need all this area that it must dissipate its heat through the fluid, or if I have a packing, through the packing, the heat transfer must occur to the sides of my reactor. So that is why, one of the reasons why, you will not build pancake-like reactors. Okay, that's a pancake there. You will not build pancake-like reactors because you will not ensure a constant to have a constant radial temperature. If I have a reactor that's not exo or endothermic at all, which doesn't happen, so if the OH of my reaction is pretty much 0, then, okay, and I don't want heat transfer, or if I want to size an adiabatic reactor, so I don't care really about the heat transfer, then that pancake-like one will work in that respect. However, one more thing that I want to warn you of is when we assume black flow behavior, right? Picture what's going to happen if I have all my catalyst here and I have the same volume, and I have all my catalyst here, and now I have a fluid that I need to distribute over my catalyst bed. Okay, chances are that if you have here, even if I just allow it to flow in and I've got packing, it's going to be nicely distributed and it will be able to in fact flow in plugs through my reactor. But in order to distribute my fluid in a fat reactor like that, I will need some form of a distribution system, and it's going to have a mixing effect. And so in this fat reactor, this will rather behave like a CSTR than a plug flow reactor. So this is one of the other aspects why it's important to have a decent L over D value, length over the diameter value for your reactor, to ensure plug flow, to ensure that I don't have any radial temperature differences. Okay, let's see if you are satisfied with my answer. Camille? That's the downsides to increasing the tube size in a nutshell. Well, not a nutshell, I probably talk too much. All right. Okay, so that's all the questions I received, and I think we're about out of time. I just have a question. I want to administer a poll, if you don't mind. Let me just clean it up. And I'm going to write my question here. And I don't want a yes or no. I'm going to ask you the multiple choice. Do you watch my videos? Not to feel guilty if you don't. I am just interested because it takes a lot of time to make them. Even if you think they are really unprofessional, it is still a stretch. But okay, so 1, yes, all. So 100% watched up till this stage. So how many of the videos have you watched up till this stage? 2, many, 2, most, 3, not at all. Okay, so let me get to my poll. Secondary content. Oh my Janneke. Sorry. Ta-da. Polling. Multiple choice. And I'm going to add a choice. And I'm going to start the poll. Can you see the poll?
Yes, we can.
Thank you. I can see you're voting. Honesty, I can't see you now. I can't see who's voting here. Okay. All right, 5 people went off to have coffee because they're not participating in the poll. They're pretending to be here, but they're not here. Let me give them 3 more seconds. 3, 2, oh, somebody suddenly, oh, they woke up. Okay, 3, 2, 1, and I am going to show the responses. Okay, I will keep on making videos. I thought you're going to give me off here, but I'm just right. And if you have comments on the videos, if you find that there's a glitch somewhere, or I sometimes say something that's unclear, please let me know so that I can fix it. Okay, they help. All right. Thanks. Okay. I wasn't fishing for compliments, but it's always nice. Right. Good, everyone. Thank you so much for showing up. Thanks, Natasha. Right. I will keep on making the videos. I will, in fact, post the content of next week's study material, the slides, as well as the videos on ClickUp today. So those of you who are ahead and you can't wait for those reversible reactions. It's really fun to work with them. I hope you find that if you suffer through the touch, if you suffer through that one and you suffer through it, you become faster at implementing it. You become better at spotting your own inherent mistakes. And if you get the pink screen, it's like, oh yes, that's what I did. I hope it becomes easier for you. Please let us know, me and the TAs, if we can help you. We really want you to do well. Okay, so stopping the recording.